Hi everyone. In this video, we'll be discussing Taylor series. In particular, we're going to expand our notion of linear approximation to approximation by higher degree polynomials. We'll define Taylor polynomials and Taylor series and practice calculating each of those. And we'll use Taylor series to better understand certain functions and certain types of series. So to begin with, I want to sort of throw back to a problem that you might have seen in a Calculus 1 course. So in a Calc 1 course, you might have been asked to say, find the equation of the line that's tangent to f of x is equal to e to the x at x is equal to 0. Now, at that time, your idea was probably, well, the slope of that tangent line at x is equal to 0, right? That's really given by f prime of 0. Right? So you would simply calculate the derivative. So you have f of x is equal to e to the x, and this is a very nice function to differentiate because its derivative is just itself, e to the x. And so f prime of 0 would have been e to the 0, which is just 1. Okay, so you would know, okay, the slope of the tangent line is 1, and you also want it to pass through the point 0 comma f of 0. So that would be 0 comma, in this case, 1, because if I plug in 0 here, f of 0 is also 1. And so now I just want the equation of a line that has slope 1 and passes through the point 0 comma 1. And well, there are a number of ways to do this algebraically, but it's fairly straightforward to see that that line, and I'm going to call this L of x, is just x plus 1. So graphically, right, what's going on, right, you had this function e to the x, say, which looks something like this. And so you came up with the equation of its tangent line, which looks something like this. Okay. Now, depending on your Calc 1 course, you may have just done that, or you could have also talked a bit about how very close to 0, this line is a pretty good approximation of the function e to the x. So for example, if you wanted to calculate e to the 0.01, well, that's fairly close to 0. It's fairly close to this point. And so the linear approximation and the actual function shouldn't be too far apart. So it's probably fairly close to 0.01 plus 1 or 1.01. Okay, so linear approximations are really useful. Now, of course, if you wanted to plug in 53, that would be a really terrible approximation. Why? Because 53 is really far away from 0. But if you're close to 0, this provides a pretty good approximation. Now, again, that's something you probably learned in Calc 1, and you probably haven't used it, certainly in Calculus 2. This isn't a notion we've made a lot of use of. You probably didn't use it particularly much more in Calculus 1, but it does come up quite a bit, and it's going to be sort of the basis for that we want to use for sort of extending to this notion of Taylor series and Taylor polynomials. Okay. So what I first want to do then is I sort of want to generalize this notion of a tangent line to something that we're going to call a polynomial. So right, a line, a linear function, is a type of polynomial. It's a special type of polynomial that's just degree 1. Okay. I want to define, given a function f, which is n times differentiable, I want to define the Taylor polynomial of degree n centered at x is equal to a as the unique polynomial p of degree n such that, so I want my polynomial and my function to have the same value at x is equal to a. I want the first derivative of my polynomial and the first derivative of my function to be equal at a. I want the second derivative of my polynomial and the second derivative of my function to be equal at a. all the way up to, I want the nth derivative of my polynomial and the nth derivative of my function to be equal at a. So the idea is, for a Taylor polynomial, I want to make sure all of these values match up to the nth derivative, right? So I want the function values to be the same, the first derivatives to be the same, the second derivatives to be the same, all the way up to the nth derivatives to be the same at x is equal to a. Okay. So if we sort of just think about this, let's first go, imagine I ask you to find the Taylor polynomial of degree 1 centered at x is equal to 0 for f of x is equal to e to the x. So what would that mean? Well, if I want the Taylor polynomial of degree 1, that means I want the polynomial at 0 to be equal to the function at 0. And I want the first derivative of the polynomial at 0 to be equal to the first derivative of the function at 0. Okay. Now, I know this polynomial is going to be a polynomial of degree 1. That means that it is going to have the form ax plus b. It's going to be a linear function. Okay. Now, I know that I want p of 0 to be equal to f of 0. F of 0 would be e to the 0, which is just 1. Okay. Similarly, I know I want p prime of 0 to be equal to f prime of 0. Well, f prime of x, the derivative of this function is just e to the x, and evaluated at 0 is just e to the 0, which is 1. So now if I was to sort of follow this idea, well, if I look here, p of 0, if I plug in x is equal to 0, that's just going to give me b. And I know from here that p of 0 ought to be 1. So my b value has to be 1. Okay, so now I know that this function is actually ax plus 1. Okay. Now, I also want to look at p prime of x. So if I take a derivative of this with respect to x, I'm just going to get a. And so that tells me that p prime of 0, well, there's no x here. This is just a constant with respect to x. So p prime of 0 is just a. And I want p prime of 0 to be 1, so that tells me a ought to be 1. Okay. So now coming back up here, I now know that p of x is equal to a, which is 1, times x, plus b, which is 1. Okay. There is my Taylor polynomial of degree 1, centered at x is equal to 0. And note, that's just the tangent line at x is equal to 0. So the first thing I want you to see is that this notion of a Taylor polynomial, when you are looking at degree 1 Taylor polynomials, they're just tangent lines. Okay. So you could say, okay, then what's the big deal? Like we're just giving a new word to the same thing. Well, now I can not only talk about Taylor polynomials of degree 1, I can talk about Taylor polynomials of higher degrees. So let's think about what would happen if we asked same function, but now we ask for the Taylor polynomial of degree 2. All right, now in terms of the conditions that need to be met, we want the function value, the first derivatives, and now up to the second derivatives to all match. But again, the second derivative of this is still going to be e to the x, and evaluated at 0, that's just going to be 1. Okay. So now I'm trying to come up with a polynomial of degree 2. Well, a polynomial of degree 2 is a quadratic polynomial. So let's say it looks something like ax squared plus bx plus c. All right, well, first I'm going to use the fact that p of 0 should be 1. So let's see if I come up here a bit. Let's see, p of 0, that's going to be 0, that's going to be 0, that's just going to be c, and that ought to be 1. So I know c has to be 1. Okay. Well, now let's take a derivative here. If I take a derivative, what's going to happen? I'm going to get the 2 is going to come down. I'm going to get 2ax plus b. plus the derivative of this c is just c is a constant, so it's 0. I mean, the constant is 1, but it doesn't matter, right? Derivative of any constant is 0. And so now when I look at p prime of 0, so I plug in x is equal to 0 here, I'm just going to get b. Oh, b has to be 1. Now, don't get ahead of yourself. You might go, oh, okay, a is going to be 1 too. But let's see what happens. Now I calculate a second derivative. Okay, so second derivative is the derivative of the first derivative. If I take a derivative with respect to x here, I'm going to get 2a, and then the derivative of b is 0. So 2a plus 0 is just 2a. And so now the second derivative at 0, at x is equal to 0, is just 2a. This is a constant with respect to x. And 2a, right, the second derivative ought to be equal to 1, which tells me that a ought to be equal to 1/2. And so now what I see is that my polynomial ought to be 1/2 x squared plus x plus 1. Now, we'll look at this more in depth in a bit, but the way to think about this is to think about this as sort of a tangent quadratic, right? Not only does it have the same function value at 0, and not only does it have the same first derivative at 0, it actually has the same second derivative at 0 as the function e to the x. Now, third, fourth, fifth, sixth, seventh, eighth derivatives, those will be different, right? Every derivative of e to the x at 0 is 1. If you try to take a third derivative of this quadratic polynomial, you're going to get 0, right? Take one more derivative of this, you're going to get 0. So the function value, the first and the second derivatives match, but beyond that, they don't. Okay. So you get sort of, you can extend this to the notion then, right, of a sort of a tangent quadratic. And you could keep doing this, right? We could play this game for a degree 10 polynomial, right? It would maybe be a little tedious if we use this approach to calculate it by hand, but you could do it. And in fact, as we'll see, once you start to recognize some patterns in what's going on, it actually becomes even not quite as bad as that. So in general, we can actually define the Taylor polynomial of degree n by this formula, which you see below. So the polynomial, the constant term will actually just be the function value at a. The constant, or sorry, the linear term will have a coefficient f prime of a, and then we'll just sort of advance term by term. Okay, so again, looking at these, you'll have sort of first a constant term, right? That constant term will just be f of a, your function value at a. You'll have this linear term, so you have this x minus a linear term, but its coefficient is just f prime of a, so the derivative at a. You'll have this quadratic term, x minus a squared. Its coefficient will be f double prime of a divided by 2 factorial. 2 factorial is just 2. But you can see that the reason we actually write it as 2 factorial is because in general, you get the nth coefficient by taking the nth derivative of your function, evaluating it at a, and dividing by n factorial. Okay. Now, to sort of see where this comes from, you can sort of imagine that we could write our polynomial p sub n of x as, I'm going to use sort of this series notation, but it's going to be a finite sum. So if I wanted the degree n term, this would be k is equal to 1 up to n. of c sub k times x minus a to the k. Okay, so really what I'm doing here is I'm just I'm sort of calling this like C0. Sorry, I should index this starting at 0. This is C0. This is C1. This term is C2. So I'm imagining for a second I don't know what the coefficients are, and that I wanted to figure out what they needed to be. Okay. Well, notice that if I just take this, and if it's the nth degree Taylor polynomial, then I want P sub n of A to be equal to f of A. Okay. So what's that going to force? Well, if I plug in A here, what's going to happen? Every one of these terms is going to be 0, except for the one that's to the 0th power, right? The one that doesn't really have a factor of x minus A. So what you get is that C0, you actually get that this is just equal to C0. So C0 has to be equal to f of A. Right, that's overlapping a bit. So that will be equal to 0, which has to be f of A. So you get that your 0th coefficient has to be f of A. Okay. And you sort of continue in this way. And if you actually just think in general about the nth coefficient, okay. So if I were to just take n derivatives of this, let's think about what would happen. So imagine if I'm just looking at, say, the second term. So I'm looking at 2 here, and my n is bigger than 2. Then what's going to happen? I'm going to take a derivative. 2 is going to come down. Then my 1 that's going to come down. This is going to become like just 1. So I'm going to have a constant term. And then I'm going to take one more derivative. It's going to disappear. So all of the terms smaller than the nth term are going to disappear. But what happens to the nth term itself? So the nth term itself is c sub n times x minus a to the n. Okay. Now what happens when I take n derivatives of that? Well, when I take the first derivative, I get n times c to the n times x minus a to the n minus 1. Then I bring an n minus 1 down. I get n times n minus 1 times c sub n x minus a to the n minus 2. Now I keep doing this. What I'm going to end up with is n times n minus 1 times n minus 2 times 2 times 1 times c sub n. And then this is going to be x minus a to the 0, which is just 1. Okay, so this is going to be my nth derivative of, this will actually be the nth derivative of p sub n of x. Now, you might wonder, how did I get the nth derivative by just looking at the nth term? Again, remember, every term lower than the nth term, its derivative was 0. So this is the only term that survives, and I want that to be equal to the nth derivative of f at A. Now, if I just take this and solve for Cn, that gives me Cn is equal to the nth derivative of f at A divided by this whole thing, but this whole thing is really just n factorial. Right? N times n minus 1 times n minus 2 times n factorial. Okay, so you see here again this sort of generic nth terms coefficient, right? It's just the nth derivative at A divided by n factorial. So what this sort of formula does is gives me a way for more quickly and efficiently computing the Taylor polynomial without having to sort of set everything up and compute everything every time. So let's actually see a bit more in practice how this works. So imagine you were asked to find the Taylor polynomial of degree 7, centered at x is equal to 0, for the function f of x is equal to sine of x. So in general, right, if you're thinking about writing out the degree 7 Taylor polynomial for this function, right, it should be f of 0 plus f prime of 0 times x minus 0, so that'll just be x, plus f double prime of 0 over 2 factorial times x minus 0 squared, plus, and I can sort of keep going through this. So the third derivative at 0 divided by 3 factorial times x cubed, plus the fourth derivative, and I'm now going to switch to this sort of prime, this other sort of notation, and I just put the order of the derivative up here. Evaluate it at 0 divided by 4 factorial times x to the fourth. Okay. And I've written out a number of terms now. You can sort of imagine what happens all the way up to the seventh derivative evaluated at 0 divided by 7 factorial times x to the seventh. All right. So what I see is that in order to really come up with this polynomial, what I need are all these derivatives. Like I need the function value and all of these derivatives at 0. All right. Well, let's start with our function, right? Our function f of x is sine of x, and I'm going to need a bunch of derivatives of it. So let me deal with that first. So if I take a first derivative, that's going to give me cosine x. If I take a second derivative, that's going to give me negative sine of x. I take a third derivative, that's going to give me negative cosine of x. Now, if I take a fourth derivative, I'm going to get sine of x again, right? So my fourth derivative, fifth derivative, sixth derivative, seventh derivative, eighth derivative, ninth derivative, 10th derivative, 11th derivative. So these derivatives sort of repeat in this cycle of 4. Sine, cosine, negative cosine, sine, cosine, negative cosine. All right. So now if we want to evaluate them at 0, well, sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0, and negative cosine of 0 is negative 1. And so now I can start to sort of plug in these values here. So f of 0 is 0. So this first term is going to disappear. So, by the way, are all the sort of the 0th derivative, the second derivative, the fourth derivative, and the sixth derivative are all going to disappear. They're all going to be 0. The only things that are left are the sort of odd number derivatives. So the first derivative, the third derivative, the fifth derivative, and the seventh derivative. Okay. So what's going to happen? I'm going to get f prime of 0, which is 1, times x, plus the third derivative, which is negative 1, over 3 factorial times x cubed, plus now the fifth derivative, so 0, 1, 2, 3, 4, 5. Fifth derivative will be 1. It'll be 1 over 5 factorial times x to the fifth. Plus now the seventh derivative will be negative 1 over 7 factorial x to the seventh. And so, I mean, I can clean this up a tiny bit. This will give me x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. Okay. This is my Taylor polynomial of degree 7 for the function sine of x at x is equal to 0. All right. I'm going to change the problem, but I'm actually going to leave this answer sitting right here because I want to look at our next problem and then relate it back to our answer we got here. So let's just make a note for ourselves, right, that this is the Taylor polynomial for f of x is sine of x centered at x is equal to 0. And I didn't write that it's degree 7, but clearly it's degree 7. Okay. So now imagine I change the problem and I ask you to find the Taylor polynomial of degree 6 centered at x is equal to 0 for cosine of x. All right. So we know we're going to need all of our derivatives, right? So we start with our function again. F of x is cosine of x. The derivative of that will be negative sine of x. The derivative of that will be negative cosine of x. The derivative of that will be sine of x. And then derivative of that is cosine, so we sort of loop back around, right? Okay. Now, if I evaluate all these at 0, then I'm going to get 1, 0, minus 1, and 0. All right. So now when I go to write down my Taylor polynomial here of degree 6, okay, so in this case, I want that p sub 6 of x. Now, what's it going to be? It's going to be my function evaluated at 0 plus first derivative times x minus a, but first derivative is 0, so that term goes away. Second derivative divided by 2 factorial times x minus a squared. Again, a in this case is 0, so just x squared. Plus, well, the next term's coefficient is going to be 0. So then we go to the to the fourth term. Okay, so this will be 1 over 4 factorial x to the fourth. The fifth degree term will be 0. And then the sixth degree term will be negative 1 over 6 factorial x to the sixth. Now, cleaning this up a little bit, this is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. Okay. Now this is the Taylor polynomial of degree 6 centered at x is equal to 0 for cosine of x. What I want to point out through these two examples is that this is a Taylor series for cosine. This is a Taylor series for sine. Sorry, a Taylor polynomial. So the Taylor polynomial here, if I take a derivative of this, oh, I know it's getting near the bottom. Let's see if I can move it up a little bit. So, okay, derivative of x would be 1. Right? Derivative of this, a 3 would come down, but then I'll have 3 over 3 factorial. Some 3's will cancel, and I'll be left with a minus 1 over 2 factorial x squared. Same thing here. A 5 is going to come down when I take a derivative, but 5 over 5 factorial simplifies to 1 over 4 factorial x to the fourth. Here a 7 comes down, so that becomes 1 over 6 factorial x to the sixth. And what I want you to notice is that this function is the same as this. Now, why is that the case? Well, this is the Taylor polynomial for cosine. This is the Taylor polynomial for sine. What's the derivative of sine? It's cosine. So because the derivative of sine is cosine, the derivative of the Taylor polynomial of degree 7 for sine is the same as the Taylor polynomial for cosine at x is equal to 0 of degree 6. So the degree of the polynomial is going to go down when you take a derivative. But because sine and cosine have this derivative relationship, their respective Taylor polynomials also have this derivative relationship. As we expand this later on, we'll actually be able to formalize that notion a bit and actually use that to our advantage quite a bit. But again, what I want to emphasize in these two examples is exactly how you write down a Taylor series, sorry, a Taylor polynomial for a given function, a given point where you want to center the Taylor polynomial at a given degree. So just a couple remarks on on Taylor polynomials. So Taylor polynomials are really good at approximating functions locally. But it would be nice if we could sort of make these Taylor polynomials go on forever, right? Like, you know, a tangent quadratic is good, but a tangent cubic is better. And a tangent cubic is good, but a tangent quartic, right? Or quintic, right? Fourth degree or fifth degree or sixth degree. Right? As the degree of the polynomial gets better, your approximation you sort of hope is going to get better. But, you know, how do we sort of make this go on forever, right? Well, the idea is actually we just create an infinite series. So we're going to take these Taylor polynomials and we're just going to extend them to have an infinite number of terms. And we'll call that a Taylor series. So given a function f, which is infinitely differentiable, the Taylor series of f centered at x is equal to a is just the power series sum n equals 0 to infinity of, if you look at this term, right, this was like the nth term of the Taylor series. Well, now you're just taking those and adding them up, starting at 0, going all the way up to infinity, right? So if you were to start writing out, you know, the first few terms of these, right, you'd see, okay, when n is 0, the 0th derivative is just the function itself. So you would just get f of a divided by 0 factorial. By definition, 0 factorial is 1. So you get f of a divided by 1 times x minus a to the 0, which would just be 1. So when 0, you just get f of a. When you put in 1, you would just get the first derivative at a divided by 1 factorial, which is just 1 times x minus a. Plus, now you just keep going, right? And so your nth term, or let's say like kth term, right, over k factorial x minus a to the k, but you just keep going, right, forever and ever, right? So this is now a power series, right? It's not really a polynomial anymore because polynomials end at some highest degree. This is now a power series, and we let this go sort of on forever. Okay, so the first thing we can do is we can just say, well, can I take this definition and sort of apply it to help me understand, you know, what's going on here? All right, so let's take a look. So imagine you were asked to find the Taylor series for f of x is equal to e to the x centered at x is equal to 0. All right, now in this case, you know that, right, one of the really nice things about exponentials, all of the derivatives are e to the x, right? The first derivative is, the function is e to the x, the first derivative is e to the x, the 72nd derivative is e to the x, right? You take as many derivatives as you want, you always get e to the x. So that tells you that the nth derivative at 0 is always going to be 1. So if we think about that formula we wrote down then for the Taylor series, now the Taylor series is going to be the sum n is equal to 0 to infinity of, well, the definition was this. Our a is 0 in this case. So it'll be x minus 0, or just x to the n. Okay? But now I know, right, all the derivatives at 0 are 1. So the sum is just the sum n is equal to 0 to the infinity, to infinity of 1 over n factorial times x to the n, or sum n equals 0 to infinity x to the n over n factorial. Okay. So this is a Taylor series for e to the x. Okay. Now, this is all sort of perfectly fine, right? We defined a Taylor series. We're sort of plugging in the information we have, right? What is a, what is the function and all its derivatives. In this case, they're all one, so it's very easy to work with. And you just sort of plug all that in and you get the Taylor series. Okay. But now remember, the Taylor series is a power series. So we can now start to ask questions about that power series, just like we did for a generic power series. So a reasonable follow-up might be to say, okay, well, now that you have this, what's the radius of convergence for this Taylor? So we found the Taylor series, but it's a power series. A reasonable question to ask would be, for what values of x does this series converge? Okay. So a quick sort of calculation here, right? If I look at the limit as n goes to infinity of, remember for power series, I'll just look at the ratio of the coefficients. So the coefficient here is 1 over n factorial. So this would be in the denominator 1 over n factorial, and the numerator 1 over n plus 1 factorial. That's all going to simplify to 1 over n. And I should be careful here. I haven't taken the limit yet. I'm just simplifying that. But now if I take the limit of that ratio, I'm just going to get 0, which tells me that my radius of convergence is infinite. And so the Taylor series converges for all values of x. And here is sort of the amazing part about Taylor series. For each x, this Taylor series converges to e of x. Okay. So that's sort of a special note. When a Taylor series converges, so you're not always guaranteed that it's going to converge for every x. So when a Taylor series for a function f of x converges, it converges to f of x. Okay. So you can write down this Taylor series for this function. It's just a power series. In general, we can talk about when a power series converges or not, but for a normal power or just a generic power series, we don't know what it converges to. But when that power series is a Taylor series for some function, you actually know that if it converges to the function itself. Okay. So this is really a really helpful and really powerful tool that we're going to take a little more advantage of later. All right. To see sort of graphically what's going on, I do want to switch over to Desmos for just a minute to take a look at something. All right. So here we actually see this function. So here this orange function is the function e to the x. And you can see I sort of have the point where my approximation is centered. In this case, I have it stuck at 0. And then right now, this is giving me the degree 1 Taylor polynomial, which is just a line. Okay. So again, you can see here, we sort of drew this picture very early on in this video, right? This is a pretty good approximation. It's a great approximation of the function value at x is equal to 0. Okay. And it also is a good approximation of the first derivative of the function at 0. And very close to 0, it's a pretty good approximation. But as soon as you get even a little bit away, right, like you get over here around like -2, the function, the linear function here and the exponential function, they're actually starting to get pretty significantly far apart. Okay, but again, our notion is, well, what if we made this a better approximation? So what if I went up a degree? Okay, so what you see here is the Taylor polynomial of degree 2. Now here, at this point, it matches the function value, the first derivative of the function, and the second derivative of the function, or the concavity of the function. You'll notice here that now this is a better approximation a little further out, right? Like sort of the interval on which this is a good approximation is larger than it was before. Okay? And so you can start to ask, okay, well, what happens as I make this larger and larger? So, right, if I start increasing this in, so cubic, quartic, quintic, right? So maybe I'll go out a couple more. So here I'm at the 7th degree approximation. You'll notice that over here, you can barely tell a difference between the exponential and the 7th degree polynomial. Although if you zoomed out, you would eventually see a difference. Over here, it seems to be a pretty good approximation, a very good approximation up to like -3. Then it sort of starts falling off. But again, if I want to get even better, right, I keep going higher and higher. You can see by the time I'm out to like 9 terms, this is now even a pretty good approximation all the way out to -4. And the idea here is that as I sort of take more and more and more terms, and as I go out in the limit to take an infinite number of terms, that's going from the Taylor polynomial now to the Taylor series, the interval on which this is a good approximation is now going to be infinite, right? Because my radius of convergence for this Taylor series of e to the x is infinite. So I can be guaranteed sort of if I go out far enough, this will be as good of an approximation as I would like. And in the limit, as I take an infinite number of terms, the Taylor polynomial really is just equal to the function e to the x. Okay. Don't be too concerned over here with what this code is. That's just some trickery I had to do to make it approximate this. But it gives you some sense of what's going on here. Now, I'll just also briefly mention, right, we've been doing this at 0, but you could also move this approximation point around, right? So you could do an approximation at, say, -2, right? If you do center your approximation at -2, it's going to look a little bit different, right? And if you think about that, that's because now it's now designed to be a really, really good approximation at -2 that carries on sort of around -2 and sort of spreads out from there. Now, again, as you go out to the limit, right, it will become equal to e to the x, okay? But anytime you only have a finite number of terms, so you're dealing with the Taylor polynomial, it'll be a good approximation for a while, well, until it's not, right? And if you sort of think about it, a polynomial, as x goes to -infinity, your polynomial is always either going to go to positive or negative infinity, while the exponential is going to go to 0. So any Taylor polynomial is only going to be a good approximation for so long before it runs off to -infinity or positive infinity. However, in the limit, the Taylor series, right, it's not a polynomial anymore. So it can actually be exactly equal for all values of x. All right. So just a couple of things to take away from that. So not only is the Taylor series converging, right, it is converging to e to the x, right, which is very important for every x value. And again, any fixed Taylor polynomial is not equal to e to the x for all x. It only sort of works in the limit, right? So that's why that's actually really the answer to the question of why are we studying power series. We're studying power series because this won't just work for the Taylor polynomials. You really have to take this sort of Taylor power series or Taylor series, right, so that you actually recover e to the x expressed as this power series. All right, let's look at another example, okay? So now I want you to imagine that you're asked to find the Taylor series for f of x is equal to 1 over 1 minus x, centered at x is equal to 0. Now, the key for these is often, right, you're going to need to figure out some way to express the nth derivative of this function evaluated at 0, okay? What you're really going to need to do is find a pattern to the derivatives, okay? So in order to do this, you usually just start computing the first several, okay? So you know your function f of x. I've got f of x is 1 over 1 minus x. Let me take a derivative. If I take a derivative, let's see, I've got like 1 over something. So that's like that thing to the -1 power. So the -1 would come down. So like if I think of this as 1 minus x to the -1, the -1 comes down, 1 minus x to the -2. So, oh, but then times the derivative of the inside piece, which is -1. So the -1 times -1 just gives me 1. I get 1 over 1 minus x squared. Now, what about the second derivative? Okay. I got to take a derivative of this. This is really 1 minus x to the -2. So the -2 is going to come down times 1 minus x to the -3, but then times the negative from the inside derivative. So I'll get 2 over 1 minus x cubed. Okay. Now, I'm going to speed up a little bit. If you compute the next one, you're going to get 3 times 2 over 1 minus x to the 4th. Compute one more. Oh, oops, it's not at 3, that's at x, sorry. X will be 4 times 3 times 2 over 1 minus x to the 5th. And so you're probably starting to see a pattern. Okay, so I want to eventually get this evaluated at 0. Okay, so, oh, sorry, not there. So let's see, what would happen if I evaluated each of these at 0? So if I evaluated the function at 0, that would just give me 1 over 1 minus 0. That would give me 1. If I evaluated this at 0, I would just get 1. If I evaluate this at 0, I get 2. Evaluate this at 0, I get 6. Might be helpful to note again that that's 3 times 2. And here I would get 24, because that's 4 times 3 times 2. And what you start to notice is that these are all factorials. This is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. And so what's actually happening here, right? The second derivative is 2 factorial. The fourth derivative is 4 factorial. So the nth derivative at 0 is going to be n factorial. Okay. So to find the Taylor series, then we just need to plug this in. So the Taylor series, right? By definition, it would just be the sum n equals 0 to infinity of the nth derivative evaluated at 0 divided by n factorial times x minus 0, in this case, to the n. And now if I just plug this in, this is sum n equals 0 to infinity of n factorial over n factorial times x to the n. That's just 1. This is the sum n equals 0 to infinity of x to the n. Now, this actually is maybe not too surprising, because if you think about this series, right, this is a geometric series. And what does a geometric series converge to? It converges to a over 1 minus r. Well, in this case, your a is 1 and your r is x. This converges to 1 over 1 minus x. Okay, when it converges. Okay. So the next question we have to deal with is sort of what is the radius of convergence of this series? Okay. So now if I want to know the radius of convergence of this series, so I'm first going to calculate the limit as n goes to infinity of the ratio of the coefficients. Okay. The coefficients here are just 1. Okay. Right? It's x to the n, and there's the only thing out in front would just be like a 1. And it doesn't depend on n. So this would just be the limit as n goes to infinity of 1 over 1, which would just be 1. That's a finite number. So that tells you your radius of convergence is 1 over that. is 1 over 1, which is just 1. And this series was centered at 0. Okay, so this converges for x values between, well, I can go distance 1 away from 0, so between -1 and 1. But now I also have to check the endpoints. Okay, now if I plug in -1, I'll get the sum -1 to the n, that diverges. If I plug in 1, I'll get the series 1 to the n, which is just 1. Adding up an infinite number of ones diverges. So this is, in fact, the entire interval on which this converges. Now, again, this should not be surprising because this is a geometric series, right? When does this converge? This converges when the absolute value of r is less than 1. So when x is between -1 and 1, this converges, okay? So what we see here is that this notion of creating a Taylor series for this function actually directly ties back to our much earlier discussion of geometric series, but it also gives you a notion of how to go through the process of generating a Taylor series. Now, moving forward, it will be nice to just know some Taylor series for some common functions. So for example, knowing the Taylor series for 1 divided by 1 minus x, that's going to be a very helpful thing to know. Knowing the Taylor series for e to the x, which we just looked at earlier, is going to be a very helpful thing to know. So we want to look at just a few more. We'll talk briefly. I won't go through a full derivation of where they come from, but some of them will look a little familiar, and they'll be nice ones to just have sort of memorized. All right. So here are a few other important Taylor series. So the first two are sine and cosine. Now, earlier, right, we wrote out the Taylor polynomials for these, and you'll notice, right, this matches exactly the degree 7 Taylor polynomial, but of course now you just keep going, okay? So here, the degree 7 Taylor polynomial, right, was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And you might wonder, how could we write that as a series? Now, when I'm looking at this, there are sort of a couple of things I'm thinking about here. The first thing I'm noticing is that we're only picking up odd terms, right? X to the 1st, x to the 3rd, x to the 5th, x to the 7th. So sort of however this works out, right, I'm going to have something like an x to the 2n plus 1, right? So notice that when n is 0, right, this is going to give me 1. When n is 1, this is going to give me 3. When n is 2, this is going to give me 5. So this is only going to give me the odd powers. And then I want to have these over that same number factorial. Okay. So again, this is going to give me an x. It's going to give me x cubed over 3 factorial. It's going to give me x to the 5th over 5 factorial, x to the 7th over 7 factorial. So you might think, great, we're done. But be careful because, right, I've also got to deal with the signs. This one's positive, then negative, positive, then negative. Now, if I want something to alternate, I'm going to need like -1 to some power. It's almost always going to be either n or n plus 1, depending on whether you're sort of starting positive or negative. So when n is equal to 0, I want to get this term, and that's positive. So if I put an n here, -1 to the 0 is positive 1. So that'll work. And then when n is equal to 1, this will give me a negative x cubed over 3 factorial, which is what I want. When n is 2, -1 squared will be positive 1, x to the 5th divided by 5 factorial. That's what I want, okay? And so here I have the Taylor series for sine of x centered at x is equal to 0. Now, for cosine of x, again, you'll see these first 4 terms look exactly like the degree 6 Taylor polynomial that we wrote down earlier, but we just need to sort of keep following that pattern, okay? So what's going to happen here, right? I'm going to get a sum n equals 0 to infinity. Unlike this one where I only had the odd powers, here I want just the even powers. So this is going to be nearly identical except I'm just gonna have a 2n instead of a 2n plus 1, right? The 2n plus 1 gave me odd terms. This will give me even terms. So when n is 0, I get positive x to the 0, which is just 1, divided by 0 factorial, which is just 1. So I just get 1 when n is 0. When n is 1, I get negative x squared over 2 factorial. There it is, negative x squared over 2 factorial. And you can sort of trace out the rest of the terms from there. Now, this last one, so these first two were for sine and cosine centered at x is equal to 0. This last one is for natural log of x, but you'll notice it's not centered at x is equal to 0. And of course, the reason for that is that our function natural log of x is not even defined at x is equal to 0, right? And we need our function to be infinitely differentiable at the place where we're centering the Taylor series. So in this case, we're going to center our Taylor series at x is equal to 1. Now, again, if you sort of look at this for a minute and think about, okay, how can I make this sort of formalize this pattern? Now, the first thing you'll sort of notice is you don't really get a 0th term here. So you could actually just start this at n is equal to 1. Okay. And you'll notice I have like a x minus 1 to the first power, x minus 1 to the second power, x minus 1 to the third power. Okay. So I'm going to have something like an x minus 1 to the nth power. And actually move this over a little bit. And you'll notice that it's here, it's divided by 1, divided by 2, divided by 3. So it's going to be divided by n. And now the last thing I need to take care of is the fact that it does alternate sign. Now here's where I have to be a little bit careful. When n is equal to 1 here, because I'm starting now with n is equal to 1, I need positive. So I'm going to make this a minus 1 to the n plus 1. You could also actually put minus 1 to the n minus 1. It doesn't matter. You just need this when n is 1, you need that to be even so that that becomes positive. Okay. So again, here you now have a Taylor series for natural log of x. This Taylor series is centered at x is equal to 1. Okay. Now, of course, one of the things you could ask then is about the radius of convergence for each of these series. Okay. So it actually turns out that for these first two, this converges for all x values, and this one converges for all x values. I encourage you to go prove that. I mean, this is a power series. You can go determine the radius of convergence. They converge for all values of x. This one is a little bit different. And in fact, this one has a radius of, well, first of all, you shouldn't be surprised that the radius of convergence is not infinite, because this is centered at 1, but you know that this this is undefined at 0. So you really don't expect this to converge past 0, right? And so if you actually calculate the radius of convergence here, you will get that the radius of convergence is 1. And so you'll get that this converges for x values between 0 and 2. If you plug in 0, this will actually become, so that will be a minus 1 to the n. This will basically become negative the harmonic series, which diverges. Again, not surprising. This function isn't defined at 0, so I don't really expect it to work at 0. If you plug in 2, then you'll just get the alternating harmonic series, which does converge. So you actually get convergence there. Okay. So again, it's nice to know some of these base Taylor series and when they converge, and we'll be able to use those to help us with more later. All right. And again, why do we care about all this stuff? Well, one of the really nice things about Taylor series is that when we recognize that a given series is a Taylor series evaluated at a particular point, it actually allows us to find the value to which the series converges. So take, for example, this series. This is like usually when we say the alternating harmonic series, we're talking about -1 to the n over n. So this is really like negative the alternating harmonic series. But say I know that this converges. I can prove this converges by the alternating series test. But the question I might want to know is, what does this converge to? Well, if I look at this, it actually turns out that this is a Taylor series evaluated, sorry, not at 1, but at 2, right? So if I look at the series -1 to the n plus 1, x minus 1 to the n over n equals 0, or sorry, n equals 1 to infinity, right? We saw earlier this is equal to natural log of x for x values between 0 and 2. Okay. So what I can recognize here, right, if I plug 2 in, this will just be 1 to the n, and that'll go away. And you might go, wait, but these aren't quite the same because you have an n plus 1 here and an n minus 1 here. But notice that -1 to the n plus 1, I could rewrite that as -1 to the n minus 1 times -1 squared. Same base, different exponents. If I add these together, I get that. Okay, so this expression is true, but -1 squared is just 1. So these two things are actually equal. They're just shifted slightly. Okay, and so what I get is that this series is really just this Taylor series evaluated at x is equal to 2. But I know for all x values between 0 and 2, including at 2, this series is actually equal to natural log of x. So what that tells me is that the value of this is actually, not only do I know it converges, the alternating series test would have told me that, but now because of its relationship to a Taylor series, I actually know what it converges to. It converges to the natural log of 2. And that is a really powerful sort of tool to have at your disposal now, right? Because now, not only do you know that it converges, you know precisely what it converges to, which is something we couldn't do before. Okay. Now, I want to emphasize one other thing. I mean, this is certainly useful, and we'll do some more of this in the next video. But another sort of thing that's very powerful about this is that we can actually do calculus on these series, right? So we sort of observed this before with the Taylor polynomials, but let's observe it also with Taylor series. So I know the Taylor series for e to the x is the sum n equals 0 to infinity x to the n over n factorial. Okay. What if I wanted to take a derivative? Right. Well, of course I can take a derivative of e to the x, right? So I just differentiate, and that's e to the x. Okay. But I could also differentiate this term by term. So if I were to differentiate this term by term, let's see, what would happen? The n would come down, x to the n minus 1. Okay. And this would work everywhere except when n is equal to 0. When n is equal to 0, this actually is just x to the 0 divided by 0 factorial. That's just 1. Okay. So when n is equal to 0, the derivative is just 0. So we actually just drop off the 0th term. Okay. And so we get this expression for the derivative. And so you might go, well, but wait, that's not the Taylor series for e to the x. But actually it is. Okay. So if we were to sort of do a little bit of simplification, the first thing we might do is recognize that n over n factorial is really just 1 over n minus 1 factorial. Okay. And now you may be starting to see that these actually do look sort of similar, but I have an n minus 1 here instead of an n, and an n minus 1 here instead of an n, and my n starts at 1 instead of 0. If you start writing out the terms, though, you'll see that actually these are equal. So here you would get 1, you would get x, you would get x squared over 2 factorial, x cubed over 3 factorial. Here, if you start and you plug in 1, you get x to the 0 over 0 factorial, which is 1. If you plug in 2, you get x to the 1 divided by 1 factorial. You just get x. So you actually get the same terms. It's just that they're reindexed. Another way to see that actually is to change the index. So say I want to let k be n minus 1. Now, if I do that, then this sum, well, when n is equal to 1, k is going to be 0. When n goes off to infinity, k goes off to infinity. And now this will be x to the k over k factorial. And now you see all these really are the same series, right? It's just this is indexed in terms of k, that's indexed in terms of n, but they're just made up names for my index, okay? Now, for e to the x, that's probably not very helpful, right? E to the x, right, you can take its derivative. But what you see here is that when you differentiate the function, right, you can also differentiate the Taylor series, and the Taylor series will be a Taylor series for the derivative as well, okay? In this case, they're the same, but this can be really helpful, as we'll see in later videos, when we're trying to construct Taylor series for more complicated functions. So we'll actually stop here for this video. The next video will be the final video of this series, in which we'll discuss, again, some more creative ways to construct Taylor functions and Taylor series using properties of differentiation, integration, and substitution.